All right, so today we're going to move forward to the full-blown standard model electroweak symmetry breaking story. So this is really very important stuff. This is the origin of mass in the universe, and it's a wonderful story. In the past lectures, we've sort of been building up towards this by studying the Higgs and studying spontaneous symmetry breaking of continuous symmetries, but also of gauge symmetries, and seeing how that can lead to the mass of gauge bosons or the mass of fermions. And all of these have been sort of piecewise steps towards building up the sort of toolkit, conceptual toolkit, because we're not doing anything that's tremendously mathematical, but building up the conceptual toolkit that will enable us to really study the standard model and understand the moving parts in a conceptual manner. I should say that the story of electroweak symmetry breaking has been absolutely fascinating. I imagine it would have been a wonderful period of particle physics to live through and to work during. It starts to some extent with the development of gauge symmetries in fundamental physics, and then things like the Higgs mechanism, the work by people like Veltman and the 't Hooft on proving that gauge theories were renormalizable, combined at the same time with very speculative sort of model building style work by Glashow, Salomon, Weinberg. And then the sort of the experimental story of really properly unraveling this picture, which essentially goes all the way back to beta decays and the Fermi operator. The experimental adventure, I like to think, was pretty much something that unfolded on European soil right here at CERN. Colliders like the SPS, LEP, principally, and then even the LHC today, have discovered the particles responsible for electroweak symmetry breaking, the particles associated with it, whether it be the gauge bosons and ultimately the Higgs boson, but also really pinned down the symmetry structure. And that really happened at LEP. I think it's one should never underestimate the scientific importance of the measurements that were performed at LEP in terms of really elucidating the symmetry structure behind electroweak symmetry breaking. So that's sort of the modern era, the theoretical development and the experimental development. But also, I mean, all of this goes right back to the very earliest times after the Big Bang. There was a moment where electroweak symmetry was broken. At very high temperatures, at very early times, the Higgs mass squared was essentially positive. And what this means is that on average, at a given point in the universe, the electroweak symmetry was not broken. And then at some point, when the temperature lowered below the electroweak scale, or even the Hubble scale went below the electroweak scale as well, there are different ways that this could have unfolded, electroweak symmetry became spontaneously broken, the gauge bosons got mass. And matter fermions got mass as well. And so this was a tremendously important moment in our sort of cosmic past. So it all ties together, and it's all tied together into one structure, which is the structure of the electroweak sector and Higgs sector of the standard model, which we will study today. Today there will be lots of equations, so I apologize. There will be more mathematical content today than in any of the days so far. That's just because, practically speaking, the electroweak sector calculations are a little bit mucky and messy, mostly because there's two different gauge groups with two different gauge couplings. But hopefully one can follow this, and hopefully my handwriting isn't too terrible that you'll be able to follow along. Okay, so we want to extend the story of spontaneous symmetry breaking to non-abelian sector. In the last lecture, we did it for U1 symmetry. Now we want to take it beyond. And so if we recall, let's say what's called the Higgs gauge sector. If you recall, now the Higgs is a doublet of SU2 and it has hypercharge 1/2. So we can write it as in the following way. We call this H1 and H2, and with hypercharge of 1/2. And so the gauge interactions look like this. They come ultimately from the gauge kinetic terms, like this. And now, what is this gauge? What is this covariant derivative, and how is it acting on the Higgs doublet? So this becomes the point at which things get really, really messy. So the first part is hypercharge acts the same on both components. It has no SU2 structure. So the way it acts in terms of a matrix acting on a vector is just with the identity matrix. And similarly, the derivative in here is the same. It acts on both components the same. But then when we get to the SU2 part, where we have the SU2 gauge fields, they will act as a matrix multiplying the vector, but that matrix will be field dependent, and it will also be have SU2 structure, so it will not be just the identity matrix. So ultimately, this object d mu acting on H will look something like d mu. Implicitly, I have this with an identity matrix plus I g prime over 2 b mu, where b mu is the hypercharge gauge field and g prime is the hypercharge gauge coupling. That thing is just, as mentioned, just multiplying the identity matrix. And then the SU2 part, so we've got the SU2 gauge coupling, which we call typical G, divided by 2, and then we've got the SU2 gauge boson. So if you recall, there were 3 of them because there are 3 generators of SU2, of the group of unitary 2x2 matrices for the unit determinant. We can choose to normalize them however we wish, really, but I'm going to normalize them in the conventional way. Okay, so let's just unpack this a little bit again. So here is just the normal derivative, the space-time derivative, where mu is the Lorentz index. Here is the hypercharge bit, so it's just got it acts in the same way. So you just got hypercharge of 1/2, so that's where that factor of 1/2 came from, and G prime, and then the hypercharge gauge field. Here is the SU2 part, and we can see the different generators. So the different generators correspond to SU2. So any of you who are familiar with the Pauli matrices will recognize this immediately. There's the 3 generators of SU2 are followed directly from the Pauli matrices. So one of them has a 1 and a -1, so we'll call the gauge field associated with that W3, and that's essentially going to lead to the abelian-ish parts of the electroweak symmetry, and it will lead to the photon and the Z boson. And then the off-diagonal parts, we would have a 1 and a -1, or an I and an I in here, or sorry, a 1 and a 1 and an I and a -I here. And so we can package those 2 gauge fields. We could call W2 plus W1, sorry, W1 plus IW2. We could call that W plus, and the conjugate we can call W minus. So that's what we're doing. But so there are 2 degrees of freedom in here, and the same 2 degrees of freedom in here. And this covariant derivative is essentially a 2x2 matrix that acts in this way onto the Higgs field. Okay. Now, when we spontaneously break the gauge symmetry, we would have a Higgs-like potential, the same scalar potential that we discussed yesterday with the Mexican hat. And as we know, we can always perform one last gauge transformation to put the whole thing into unitary gauge, where the Goldstone bosons are eaten by the gauge fields, okay? And there's no point going through that whole process for this story because we saw it yesterday, and it follows through in exactly the same way. So we've got the Mexican hat potential for H. This is the potential that looks like, I say Mexican hat, so it sort of looks like this. And the Higgs wants to roll down to this point out here, which does not, it's a vacuum which does not respect the SU2 cross U1 symmetry. And we can perform one last gauge transformation such that the Higgs field in this vacuum, we can accurately describe it as 0 and V plus H over square root 2. Okay, So we've done that last gauge transformation to go to unitary gauge, and we can see that the three Goldstone bosons that have been eaten were here. There were 2 in here because it was a complex doublet, 2 degrees of freedom here, 2 degrees of freedom here. So we've lost 2, but we should lose 3. And you see that we've lost the imaginary part in here. This part here is entirely real. V plus h over root 2, and h is the field, little h. So little h is the last degree of freedom. So indeed, our 4 components of the Higgs field have led, after electroweak symmetry breaking, once the gauge fields eat the Goldstone bosons to become the longitudinal components of the gauge fields, we've got 4 minus 3, so we're left with 1 physical field left over, and that's the Higgs field. Okay, so now we can use some, I'll stick with red, we can use some tricks to basically pick canonically normalized fields, because when we put this guy into here, so I can actually, let me just rub that out and do that. So the way this is acting in terms of, once we've done that last rotation to unitary gauge, it looks like this. We've got acting on this 2 by 2, sorry, this 2 row vector, v plus h over square root 2. And now we want to see how these guys act across onto here. So to make that a little bit more clear, we can choose the blue is probably clearer. We can choose a normalization for the gauge fields, which will just make our lives a little bit easier. And the conventional normalization to take, and you'll see why this is to call the electromagnetic gauge field for QED, A mu is G B mu plus G prime, sorry, W3 mu divided by G squared plus G prime squared to the half. And Z mu, which will be the Z boson, is G prime B mu minus G W3 mu over G prime squared plus G squared to the half square root. So why do we do that? We can see that if we stare at this equation here, the component that's acting on the sort of the 2 component down here, that's acting on here, goes like G prime B mu minus G W3 mu. And that's exactly this linear combination, G prime B mu minus G W3 mu. So the thing that's going to get mass from the Higgs is the one that's in the 2 component and these guys here, but not this component, because if you look at this matrix, the 1 component acting on here, you just get nothing. So we take one linear combination, which is the one that's going to get mass. That will be the Z boson, which is G prime B mu minus G W3 mu. And then the other linear combination, because we still have the kinetic terms, these are canonically normalized propagating fields. So we have to choose a field rotation between B, W3, and A and Z, which is an orthogonal transformation if we want to keep the kinetic terms with the standard normalization, so that these fields propagate in the normal way. And so once we've chosen that linear combination, we have to canonically normalize it. So that's this thing here. And the only allowed other linear combination for an orthogonal field, so something that won't then mix in the kinetic terms, is this one here. You see it's completely orthogonal to this. And you can already see, we're going to discuss this in a second, but you can anticipate that you can really consider these things, this to be a rotation where we have something like A mu Z mu is equal to a rotation B mu between these two fields, which is completely orthogonal. And then it would be cosine of theta omega sine theta w, where this is the Weinberg angle that we will come back to, minus sine of the Weinberg angle, cosine of the Weinberg angle. So you see that this is an orthogonal rotation. This is just a rotation matrix between the two of them. So we're sort of, the kinetic terms pin you down to only allowing that if you want to keep canonically normalized fields. Okay, so now let's just plug this in and see what we get. So when we plug this into this term here, we get the following thing. So we get d mu of h onto h is the little d mu again, plus I g squared plus g prime squared to the half over 2. And then we've got some things go 0, 0, and z mu. And some things up here, I'll do some little red dots that we will come back to what's in this component up here. Plus IG 0 W minus mu 0 W plus mu acting on 0 V plus H over root 2. Okay. So finally we can multiply this through and we'll just get a two row vector. This will eventually come to be 1 over root 2. The derivative acting on V is just the expectation value of the Higgs, gives you nothing. So we get nothing from the derivative there, and all we will get is 0 and d mu of little h. And then here we will get I v plus h over 2 root 2, and then a two row vector g w plus mu, then some horrible mess g squared plus g prime squared to the half z mu. So finally, when we put this whole thing together and study the kinetic term of the Higgs, we have that the modulus of d mu h all squared is equal to 1/2 d mu little h all squared plus, I'll write it down here, right over here, plus v plus h all squared divided by 8 multiplying 2g squared magnitude of w plus mu squared plus g squared plus g prime squared multiplying z mu squared. Okay, so we see here that we're going to get from V alone, we're going to get a mass term for the W plus minus and a mass term for the Z boson. And in fact, we can just see what they are just immediately. From this way, you can read it off because the mass term is essentially the coefficient after differentiating twice. It's the coefficient of the quadratic term for these fields. So we get that MW is GV over 2, and MZ is G squared plus G prime squared to the half V all over 2. So this is how the W and Z bosons got their mass. It's really that simple. Now, as I said, it's a little bit mucky because there's not abelian. There's two different gauge groups. There's two different gauge couplings. So it's not, some super minimal, highly symmetric scenario. Nonetheless, it works. Okay. And we can now go ahead and calculate many, many interesting things from this. So let's see. So what I will do is let's go back to these little red dots here and calculate what's going on in there. So what's the bit living up the top of this this matrix? Because it didn't enter in here anything that was at the top. When it multiplies onto 0, you just get 0. So we could leave it out for the purposes of finding the W and the Z mass. We didn't need those terms. However, those terms are still relevant because that piece up there is what corresponds to the photon. Right, we started with W3 and B mu as the two neutral gauge bosons. And they gave us Z mu, which is the Z boson, the thing that we know and love, the particle we know and love. Well, what's up here? It turns out it will be essentially the photon. But what we had up there was not so simple, right? It was G prime B mu plus G W3 mu. And we can write that, you can do this as an exercise if you wish. G prime B mu plus G W3 mu is equal to 1 over G squared plus G prime squared to the 1/2 multiplying 2 G prime A mu plus G squared minus G prime squared Z mu. So that's actually what is living up in these red dots here. And so we can see that A mu acts on the top component of this vector with a strength proportional to 2 G prime over G squared plus G prime squared to the 1/2. And that 2 actually cancels this factor of 2 in here. So so that 2 cancels that factor of 2 in here. I think I've missed the factor of this G squared plus G prime squared in the numerator there. So that's not exactly what's in the red dots here. Okay, so I was starting to dog in. Okay, so from this we can then go ahead and calculate how strongly the photon couples to the top component of any representation, which is fermion or scalar, for instance, which is in the representation of hypercharged 1/2 and a fundamental doublet of SU2. Okay, so we see that will correspond to the photon, which is the coupling to this guy here. So we see that E, the electromagnetic gauge coupling, will be G prime G over G squared plus G prime squared to the 1/2. Okay. And so it makes sense when you look at this formula for the W mass, the Z mass, and then the electromagnetic gauge coupling, which is predicted in terms of G prime and G. Then we get, it makes sense, it's sort of crying out for an interpretation in terms of angles. And so the Weinberg angle is defined through sine of theta Weinberg, W, is equal to G prime over G squared plus G prime squared to the 1/2. So then we find that the electromagnetic gauge coupling is G sine theta Weinberg and MZ cosine of theta Weinberg is MW. So these are very universal relations. And finally, we can write now in this notation with these angles, we can simplify all of this stuff up here in the following way. So now the covariant derivative acting on the Higgs doublet takes the following form. So d mu acting on H is d mu acting on H plus I G sine of theta Weinberg A mu plus cosine of 2 theta Weinberg over 2 cosine of theta Weinberg Z mu. So that's the first component. I'll put a wee comma just to remind you that. W plus mu, W minus mu, and then in here there's a Z mu over 2, over 2 cosine theta Weinberg, all multiplying H. So these are the gauge interactions of the Higgs field. Mind you, we could have started out parameterizing it in this way, and we would have gotten to the final result very, very quickly and easily, because we would have gotten, if we put in the V plus H in here, then we would have gotten everything out straight away without all of this algebra. However, I wanted to show you from the algebra, starting with the 2 gauge groups, for which the interpretation is not clear at all here. to really show how this structure emerges from a more unified structure. We call it electroweak unification, because in the UV, at high energies, small distance scales, the theory has two unbroken gauge symmetries, essentially. It has the hypercharged gauge symmetry and the SU2 gauge symmetry. And then when Higgs gets a VEV, and you can almost, in your mind, put a timeline to this when you embed it within some cosmological history. When Higgs gets a VEV, this vacuum expectation value V, which is all the way out at the bottom of that Mexican hat potential, those two symmetries are broken together, and only one is left over, which is QED, the electromagnetic gauge symmetry, which is responsible for most of the phenomena we see in nature and anything involving electricity or magnetism. So it was really, in my mind, this is really an enormous intellectual feat, right? It shows that QED itself is not a fundamental thing. It's more, at best, and this may not even be true, but at best it would be that hypercharge and the electroweak gauge symmetries are more fundamental than the gauge symmetry of QED. And that follows from essentially a unification above the electroweak scale into those two gauge forces. But one can also ask, what does that unification get you? And it really gets you an awful lot. So, because whenever we use the words unification, it should, underneath everything sort of imply some sort of simplification or larger constraint placed on theory than if you didn't have that unification. And indeed, that's what happens here, because essentially, if you can measure, and this all follows through. I'm not going to go through the details of this again because we did it in terms of an abelian theory yesterday, and it all follows through in the same way. But if you could measure, for example, and there are equivalent sets of measurements. You can measure the gauge bosons and one gauge coupling, or you can measure the Higgs mass and things like this. But if you could measure the four parameters V, G, G prime, and MH, or equivalently, well, we're going to use V because you can extract that from beta decay directly from Fermi's constant. That's essentially Fermi's constant. G Fermi is something like 1/8 root 2 V squared. And then M, actually maybe let's do, well, you could equivalently measure E, MW, and MZ, and MH. These might be parameters that seem more physical to you because you can measure a mass, these different masses. So these are equivalent set of measurements. From these, you can rewrite all of these in terms of these. And once you measure these things, everything else becomes set in stone. And that means that, every other physical prediction you might want to calculate of this theory, so, some scattering amplitudes or some event rates at the LHC or some other colliders, or even the electroweak, 2-loop or 3-loop corrections to some process, maybe it's some low energy flavor process, something like the mu-anomalous magnetic moment corrections, all of these sorts of things become very much set in stone in terms of the electroweak sector once you've measured 4 of these parameters. These ones are sort of more fundamental in the sense of, you can wrap them up in many different ways, in the sense of the scale of electric symmetry breaking in the gauge couplings. So if you were to measure, and you could even replace MH with once you have V with the quartic coupling of the Higgs, for instance. As in some sense, the UV story would have lambda H. This is all equivalent. And the IR story, we would measure, for example, the electromagnetic gauge coupling and the masses. But in practical terms, quite often the parameters that we use, and these are the ones that you will see if you're putting things into loop generators for MATGRAPH or something for predicting collider processes, most frequently we take the set of parameters that we can actually measure the best, Oh, by the way, if you didn't have the Higgs and you were just talking about the electron weak sector, you'd only need a set of 3, so V, G, G prime, or E, M, W, M, Z, if you're talking about processes that don't involve the Higgs in any way. But now I think it's fair to package the Higgs with them, because we've discovered the Higgs, so we've really completed this story of electroweak symmetry breaking in terms of experiment. This might seem more physical, because it's like the electromagnetic gauge coupling, which we all know and love, and then a bunch of masses, which correspond really to poles in scattering amplitude. So you can see it as a peak somewhere. The Z peak is very clear, and we all know the famous M Higgs peak. Practically speaking, though, if you want to do the most high precision calculations possible, you want to take the inputs that have the highest precision possible, and that tends to be the electromagnetic gauge coupling measured at some scale. All of these parameters run under RG evolution, which you may have heard of. So electromagnetic gauge coupling measured at some fixed energy scale to really high precision, and then actually V, which is equivalent to Fermi's constant, because we've measured things like beta decay rates or muon decays extremely well. So actually Fermi's constant, which is equivalent to V, can be extracted to high precision. The W mass is harder to measure to high precision. It doesn't really show up in a pole of a 2-to-2 scattering process, an S-channel pole of a 2-to-2 scattering process, when the 2 initial state particles have a charge that sums to 0, because it has charge 1, so it's not going to show up in that way, which means that it's normally, the W mass is normally extracted from sort of the tails of distributions, the sort of turning points of and broad features of distributions in processes that involve a larger number of particles. And so it's not quite as well measured. So we usually replace MW with V, which is better measured, and then MZ, and now that we have the Higgs and MH. We have not got anywhere close to directly measuring the Higgs quartic coupling. So we couldn't use that as an input, whereas we have measured the Higgs mass to extraordinarily high precision. Okay, so that wraps up the electroweak sector and the sort of the structure of electroweak symmetry breaking with some quantitative aspects. We're not being too sloppy with the mathematics. I think one thing that is a little bit sloppy, I think, compared to last year's lecture notes, I'm using a convention where the gauge fields, the covariant derivative has an opposite sign involving the gauge fields. So you might need to put a -1 if you're comparing with the lecture notes from last year. You might need to put a -1 through everything. But apart from that, I think it's pretty much the same. Okay, so now that we've done the electroweak gauge sector, now this is, as I said before, I'm approaching this in a slightly opposite direction to what we would normally, the way we would normally see it presented. Often we would see these things presented more from a historical perspective, and then sort of building up, culminating in the Higgs. And as you can see, I've sort of jumped the gun by going straight into the Higgs sector, with the hope that then you'll see its sort of unifying role within the structure of the Standard Model. And what we're going to do next is something that we would normally, I think, from a more chronological perspective, do first, which is leptons. Now, the lepton sector of the Standard Model is sort of simple, and the reason for that is that it's perturbative. There are no big, strong couplings in the lepton sector of the Standard Model, and that means that one can calculate physical observables from a perturbative perspective. As long as you get the first one loop quantum corrections, for instance, then in terms of electroweak physics, you've done very, very well. But also, we don't have particles that are binding together and confining like we do have in QCD. So everything behaves very well as well. And note that these things are sort of quasi-decoupled. We can, to a large extent, not entirely, we can to a large extent discuss the lepton sector without really having to discuss QCD very much at all. And that's because the couplings are perturbative. So even if there are strongly coupled things going on in the QCD sector, the lepton sector remains sort of okay and largely untouched. And that is something you'll be familiar with. We don't really talk about, you know, we're happy to talk about the physics of electrons at very low energies and at very high energies in sort of the same, using the same sort of dictionary. Whereas for QCD, which we will come to next after leptons, we can't really use the same dictionary at low energies. There's no such thing as a quark or a gluon because they're confined. And so your language for QCD at low energies involves things like pions and protons and baryons. And yet to go above the QCD scale, it completely transforms into a discussion about quarks and gluons and things like that. So leptons are sort of simple. And the electroweak structure of leptons is very interesting. And finally, the leptons themselves have their own little puzzle, which is related to neutrino masses, which is something that does not show up in the quark sector and actually distinguishes leptons very much from the quark sector. Okay, so enough blah, blah, blah. Let's get on with leptons. So all of the leptons we know and love are the electron and positron, E plus minus, and in terms of flavors, not mass eigenstates, the electron neutrino. Also, sorry, that's my dog who's just here. Also mu plus minus and the muon neutrino, and then tau plus minus and the tau neutrino. Some comments on this, you know, I would say that here is where quantum field theory arguably began. You know, in the early days of quantum field theory, physicists, for example, like Dirac, were really wrestling with the Dirac equation and the interactions between electrons and positrons and photons, and trying to build a quantum theory. And it was only really, you know, essentially Feynman, Tomenaiga, and Schwinger, who put that on a firm footing, and really Dyson as well to a certain extent. And so that all began with the story of QED. So it's nice, you know, I think thinking about leptons, one should remember that this is really the starting point of quantum field theory. The muon was also something which famously, when discovered, it was discovered in cosmic rays. There were, and I really strongly encourage you to go and look at these experimental papers. They're really beautiful because they have these tracks for the cosmic rays, and they say, well, you know, this thing sort of looks almost like a proton, except it has a similar mass, similar charge to a proton, but it has a mass which is implied by how much the track was curving according to the magnetic field, a mass which is something like 10 times less than the proton. This was enormously confusing at the time. And it's very reminiscent of modern day particle detectors, actually, that even those old photos from like, I can't remember when, 30s or 40s. And Rabi famously said, who ordered that? When it was discovered. And indeed, you know, we still don't even really know why it was ordered. We cannot answer his question yet. We don't know why there's 3 generations and so on. The tau, that's sort of like a double, who ordered that? And then the neutrinos themselves have been a rich source of interesting physics and particle physics that connects to many things like the history of the universe, the functioning of stars, and so on. And then neutrinos have indeed their own unsolved problem, which is the puzzle of neutrino masses and what the microscopic origins of those neutrino masses are. Okay, so let's consider the gauge and Higgs interaction. So now I'm just going to focus on the electron, the first generation, sorry. So the electron neutrino. So we consider the first generation. The Lagrangian looks as follows. I EC dagger D slash EC plus I L dagger. I'm going to explain what these things are in a second. So what is EC? EC is, these are both Weyl fermions, which I always work with. And so EC has hypercharge 1. So d mu is just partial d mu plus I g prime b mu. But recall that b mu was cosine of theta Weinberg A minus sine of theta Weinberg Z. So let me just write this in. So this thing here is actually cosine of theta Weinberg A mu, where A mu is the photon, minus sine theta Weinberg Z mu. So that means then that and remember that G prime cosine of theta Weinberg is equal to G sine of theta Weinberg, which is equal to E, the electromagnetic gauge coupling. So in terms of Feynman diagrams, the interactions between EC and the photon are as follows. EC dagger, now coming in, now we're going right, EC, and then the electromagnetic gauge coupling here. And the interaction with the Z boson takes this form. Okay, so the fact that this thing is super simple, it's not in an SU2 multiplet, it's just a singlet of SU2 with hypercharged 1, completely fixes the interactions with this vial spinner, which I'm calling EC, E conjugate, and the photon and the Z boson. Okay, so now let's go on to L. So L was a doublet, an SU2 doublet, and it had hypercharge a half. But we can recall, I shouldn't have rubbed it off. We can recall the interactions. This thing has exactly the same quantum numbers as the Higgs boson, essentially. And so what that means is that we can take that covariant derivative that we had for the Higgs boson and transport it into being the covariant derivative for the lepton doublet. Okay, so doing that, we will write L is equal to, let's call it EL, sorry, that's my dog, nu E. And using that exact same covariant derivative, so you can go back and just look at that, there's no need for us to go through the derivation again. Then the interaction with the charged current, because the charged current interaction, essentially the interaction with the W boson, is E dagger L nu E, and then G and W minus mu. And the neutral interaction, so you can see that that's just the electroweak SU2 gauge coupling. The neutral current interaction, which I'll call NC, it's normally called NC, will involve, we need to study the neutrinos and the EL, which we call like the left-handed electrons, those are the electrons that are in the doublet. And the coupling of the neutrinos, a neutrino to the photon, A mu, is this. And this came from the fact that G prime B mu, how can I say it in words? This thing, if you recall that the Higgs was in the lowest component of the Higgs doublet, and that Higgs had no coupling to the photon, and that's exactly the same reason because the photon was in the 1,1 component of the covariant derivative, and it's for exactly the same reason that the neutrino has no coupling to the photon. What about the Z? Well, the neutrino will have a coupling to the Z because that's in the 2,2 component. Move Z mu, and then move G over 2 cosine of theta Weinberg, nu E dagger nu E. And then I'm going to have to cram these in a little bit. I'll rub off actually the charge current interaction. And now we need to look at the electron interactions. So the EL dagger EL interaction with the photon, again, just following directly from that covariant derivative, is E. And the one with, for exactly the same reason that we saw that for a spin, the covariant derivative for a hypercharged 1/2 SU2 doublet, that top left component was E times the photon. And then finally, the interaction with the Z boson, Z mu, EL dagger, EL minus G prime sine theta omega plus G over 2 cosine theta omega. Okay, so these are in Feynman diagrams. These are all of the interactions that have come out of those covariant derivatives. Now, the thing to note here is that the left and right-handed, so we sometimes refer to this as the right-handed and left-handed components of the electron coupled to the photon with the same strength. So that's a good start. It means we say that then that interaction is vector-like. It doesn't care about the left-hand and right-handed components, because ultimately, once the Higgs gets mass, once the Higgs gets a BeV, there will be in here, we will see this when we do it, but in here, the Higgs coupling, which will look like YE Higgs LEC, will give a mass which is ME ELEC. And so ultimately the mass, so the Dirac spinner that we're going to come to in a second, is made up of the left and the right-handed components. And we see they interact with the photon in exactly the same way, which is great. But the Z boson does not interact in the same way. Here we have minus G prime sine theta omega, theta W. And here we have minus G prime sine theta W, the same. So there's a part which interacts in the same way. But the left-handed guy has an additional G over 2 cosine of theta Weinberg, meaning that this interaction is chiral. It is not vector-like. There is a part of it which discriminates between left-handed and right-handed electrons, which is a really, really profound thing, you know, and is linked ultimately to parity violation in particle physics. Okay, and I think given the timing and the I'll just finish this with Dirac notation. So let's go back to Dirac notation. We discussed it a little bit in the past, but not with any great detail. And we'll just finish up with this the last couple of minutes. Okay, so as I mentioned in the last lecture, or maybe 2 lectures ago, you know, if you're working with vial spinners and they have a mass that respects the chiral symmetry, then you can write that equivalently as being a Dirac spinner. It's exactly the same thing. All the physics is identical. It's just really a choice of conventions, really. And we can write our Dirac spinners as, let's call our Dirac spinner E. So we can write that as EL and EC dagger. And then PL acting on E just gives you EL and 0. So these are projection operators. You can think of it in terms of a matrix as being something like 1, 0, 0, 0. And P right acting on E will give you the other component, EC dagger. So this is just a way of packaging these 2 vial spinners together into one Dirac spinner. Clearly, PL plus P right is the identity, and PL squared is just PL. You square this matrix and you just get the same matrix back, and P right squared is P right, but PL P right is 0. And so we see that in terms of Dirac notation, if we're writing it in this way, that then these interactions, which is maybe how you're more likely to see them in textbooks, for a Dirac electron, so now I just call it E minus and E plus. For a photon, it's just E. But for a Z boson, we get this extra projection operator, which wants to pull out some additional dependence on sine theta omega. That was the universal bit. And then the projection operator, 2 cosine theta omega with PL, where that's the left-handed projection operator. And similarly for the interaction of the W boson and the neutrino and the electron. Okay, and I think I should leave it there. This is a good moment to leave it. And in the next lecture, we'll come back and begin by considering leptons and Higgs. And we'll do actually a short exercise to see how many Higgs bosons we expect to decay into muons just using some basic scaling properties of the Yukawa interactions, how many Higgs bosons decaying to muons we expect to see at the LHC. And I'll leave it there. Thanks.